Okay, so bit of a difficult situation yesterday. Was anybody able to get anything out of the recording that I sent out, or was it universally too blurry?
Listen to what you said.
Later it got better. Okay, well, yeah, so I think we'll just do a significant recap today. Don't worry, none of that is on the quiz, right? Don't forget there's a quiz at 3. That will take 24 hours. Well, it shouldn't take you 24 hours. You have 24 hours to do it. Right, so what was the last thing we did on Monday then? We reviewed level sets, right? Is that where we talked about some specific examples? We talked about how the level sets of a 3-dimensional sphere look like 2-dimensional spheres of various sizes, right? When we set our level set equal to a positive number. There's just the point 0. Yeah, we did a bunch of examples of level sets on Monday, right? Okay, so I think we came just shy of describing the definition of what a tangent set is to a level set, right? We didn't talk about that on Monday. Is that correct? And yeah, you might have heard me talking about it in the recording. So let's start there. Right. Okay. Theorem. Let's suppose f of x hat is continuously differentiable. Real valued on an open set around some point P hat a vector in Rn. And we'll also assume that the gradient of f evaluated at P is not equal to the 0 vector. Then near P, the level set M through P, i.e. where f is equal to f evaluated at P, right? Again, remember, we specify a level set by setting the function itself to a constant. We can generate that constant by evaluating our real valued function at some vector P hat. That's what we're indicating here. The level set M through the point P looks smooth, which is another way of saying no singularities, no sharp points, no places where we can't define the tangent set. And is n-1 dimensional, right? Okay, so f we can deduce is a function of n variables because P is in the domain, right? And it's a n-dimensional vector. And it's real valued, so that means the graph of f lives in n+1 dimensions, and it is an n-dimensional thing. And when we take a level set, as long as it's continuously differentiable, we get something of dimension n minus 1. Right? A function of two variables has a graph that's a surface. You take a level set, as long as it's continuously differentiable, the level set is a curve, something of dimension 1. Right? Okay. So a vector v hat based at p hat. Remember, vectors are translation invariant, so I can take an arbitrary vector and slide it around till I get its initial point at p hat. That's what I mean by based at p hat, right? Such a vector based at p hat is tangent to m at p, if and only if the gradient of f evaluated at p dot v hat is equal to 0. So the tangent set to m at p is the set of all vectors x and Rn, so that the gradient of f evaluated at p hat dot x hat minus p hat is equal to 0. Okay, so what are we saying here? The gradient is always perpendicular to a level set, as long as our function is continuously differentiable. Again, a fairly mild assumption. Okay, so just as in calculus 1, where we used the derivative to define the tangent structure, which happened to be a line for curves, so we now use this generalized notion of the derivative, the gradient, to define the tangent structure for a given level set. Okay, so at this point, I want to emphasize that we had already defined what a tangent set is to the graph of a function. We're doing something slightly different now. We're defining what a tangent set is to the level set of a function, right? So these different perspectives will be useful to us at different times. So it's kind of important to keep them distinct in our minds, even though the definitions look very much the same. And in a certain regard, they are interchangeable. But depending on the type of information you're given, one or the other definition might be more useful to you or easier to apply. Okay. All right. So to wit, note if m just so happens to be the graph of a continuously differentiable function, continuously differentiable, then this coincides with the old definition of tangent set. right? That is to say, we're defining M as a level set of the function capital F. If there's some other function G that happens to have M as its graph, right? So if F is a function of n variables, then G would be some function of n minus 1 variables. Then this definition matches the first definition that I gave you last week of tangent set. Okay. All right. So let's do some examples. The above theorem with n equals to 2 gives what? What happens when n equals 2 in the hypothesis of the theorem? The level set will be in one dimension, and the tangent set will then be, say again. Okay, so if the level set turns into a level curve, something of one dimension, what will the tangent set become? Yeah, a tangent line. Yeah. Okay, so in particular, tangent line to a level curve through some point P, which now will give coordinates a comma B, since n is equal to 2. Right. So what do we get here? Gradient of F evaluated at a comma B dotted with x minus a comma B zero, and x of a comma B, comma f y of a comma B dot x minus a, y minus b. Here I've used the notation x hat for the vector x comma y, right? Our vector of variables. Okay, let's actually calculate this dot product. And there you have it, a standard equation of a line, right? Verifying what we deduced just from dimensional analysis, right? Just at the outset, we were like, okay, we have two variables. That means our graph is a two-dimensional thing that lives in 3 dimensions. Take a level set. It happens to be continuously differentiable, right? By the assumption of our theorem. We take the level set, the one-dimensional thing, and the tangent set should be aligned. And if we apply the definition, that's exactly what we get. Standard equation of a line. Where I guess I should say, again, agreeing with the theorem, where we had assumed the gradient of f evaluated at a comma b was not equal to the 0 vector. Okay. What happens when n equals 3? And again, this time we'll take the assumption outright. Our gradient is not equal to the 0 vector. What are we going to get as our tangent set of the level set through the point a comma b comma c? Yeah. So right, remember a tangent structure is always a linear type thing or an affine linear thing, right? So a level set will become a curve for 2 dimensions, or a surface for 3 dimensions. And then the tangent set will become a line or plane or space, right? Tangent things are always linear things. Okay, so when n equals 3, the theorem gives a tangent plane to the level curve. I'm sorry, level surface through the point A comma B comma C. Right? i.e., when we compute the dot product, we just get the standard equation of a plane, right? Where our normal vector, again, remember in the standard equation of a plane, you read off the coefficients of your variables to get the normal vector. This reiterates the fact that the gradient is normal to the level curve at all points, as long as your function is continuously differential and the gradient is not zero. Yeah, just another way of seeing that. Okay. So here's another example. These are very general examples, these two that we just went through. Now let's actually choose a particular function and see what's going on. Okay. And we're gonna return to this example quite often because it has this behavior of, well, I should say much more about that now. We're gonna study this function a few more times throughout this term. Okay, so first of all, this is continuously differential, right? It's a polynomial. You can take its derivative infinitely many times. That means its derivative is differential, therefore definitely continuous. Okay, so what's the gradient of f? Yeah. 2x comma negative 2y. Good. Okay. So gradient of f is equal to the 0 vector only when? Only when x equals 0 and y equals 0, right? So that is to say, our theorem applies everywhere except 0, 0. Right? Okay. Like all level curves through points other than points f equals 0 are smooth, meaning, of course, we've said a bunch of different things for what smooth actually means, but here, what we mean by smooth is that we can define a tangent set in a coherent fashion. Say uniquely what the tangent set is at any given point on any level curve other than this one. So, right. Why don't we, for example, look at f of x, y equals 1. Okay, we graphed this on Monday. You can remind me what the graph of this looks like. Yeah, yeah, it's a hyperbola. Here's f of 1. And why don't I look at some specific points on this level curve? So at point, why don't we say 1, 0. So why do I pick this point first of all? What's special about this point relative to everything that we've developed so far? Yeah, it's on this level set that we're considering, right? Okay, so at this point, the gradient of f evaluated at this point is just 2, 0. Okay, so turning to our graph, here's our point 1, 0, and our gradient vector based at the point P, right? I'm going to move the vector 2, 0 so that its base point is at the point I chose, 0, 1. Get this vector 2, 0. Okay, this is encouraging. What's the tangent line at this point? Yeah, it's the vertical line x equals 1, which is perpendicular to the gradient. Yeah. So let's bear that out in computation, right? So the tangent line is given by the gradient evaluated at our point dotted with x comma y minus our point, right? X minus 1 comma y minus 0. Okay, and what do we get here? We get 2 times x minus 1 plus 0 times y equals 0, which a little bit of algebra will confirm what was already said. This is just a line x equals 1. Gradient. All right, why don't I pick some other point on this level set, or that this level set passes through? For example, we're going to take root 5, comma 2. And verify that this, in fact, goes through, is on the level set. Yeah.
The tangent line and the gradient are.
When you can define the tangent line, yes.
Okay, so essentially. So
Sure, you want to say?
well, I was just gonna say, so if they're always.
Yeah, that's it. That was exactly our theorem, right? That the tangent set is defined by the set of vectors that are orthogonal to the gradient. Yeah. Okay, good. What's the gradient of f evaluated at root 5 comma 2? Well, you just get 2 root 5 comma negative 4. Okay, so then we get the tangent line just as follows. Gradient of f evaluated at root 5 comma 2 dot x minus root 5 comma y minus 2, which is just equal to 2 root 5 times x minus root 5 plus 2 times y minus 2, 0. All right, let's look at this graphic. Square root of 5 is something more than 2, right? Or like here. And our gradient vector is 2 root 5 negative 4. So looks like this. Right? Obviously the magnitude is not to scale, but you get the idea, I think. And then again, our tangent line, just this line, which is perpendicular to the gradient. Okay. Gradient of f root 5 comma 2. Here's our tangent line. Again, my drawing's not very scaled, but this should be a line of slope root 5, right? Yeah. Oh yeah, sorry. Good catch. Plugged in the 2, not actually the gradient evaluated at the root 5 comma 2. Good. Yeah, so then in fact the slope is negative root 5 over 2, right? Which is much more consistent with the picture. It's this line of negative slope, right? Okay, good. Okay, so when the gradient of a function happens to be the 0 vector, that's an indication that we might not be smooth at the level set that goes through that point. Right? For example, with the function we were just looking at, what happens at the level set x equals 0? I'm sorry, f equals 0. What level set? What does that level set look like? We also discussed this on. Right? When you set x squared plus minus y squared equal to 0, what do we get? Yeah, we just get the pair of asymptotes. This is f0. So it's no coincidence that when we have the gradient equal 0, we get this non-smooth behavior, this crossing here. Yeah.
I forget what the-
Well, what do you mean? The gradients are always perpendicular to the tangent lines. Okay, so what you're asking is as what goes to infinity?
as
For a particular level set, you're asking. Okay. So well, your tangent line will in general cross the asymptote, right? Because it doesn't curve. Whereas the actual level curve comes closer and closer and closer to the azimuth. It curves away from it. So at any point that you draw the tangent line for, it will cross the azimuth at some point.
Even if it's at,
Well, what do you mean by at an infinite value? That's not a well-defined thing to say, unless you make some definitions to say what that means. So yeah, this is more like just the end behavior of a single function. Really interested more in like the family of functions that consist of all the cross sections of the surface in this case. Okay. The point being that where the gradient is 0 in this function, we have this non-smooth behavior, right? So we want to characterize exactly the relationship between the gradient being 0 and finding non-smooth behavior. Okay, so again, let's suppose x hat is continuously differentiable. Real valued on U, an open subset Rn. If T hat is a singularity on the level set, f of x equals f of p, then the gradient of f at p must be the 0 vector. Okay. Notice that this is not an if and only if statement, right? That is to say, if we know that the gradient of f at p is 0, that does not imply that the level set through p is singular at p. But if it is singular, if we draw the graph and we see some behavior like this, some sharpness, then necessarily the gradient must be 0 at that point. Okay, so that kind of motivates this definition. We take again f of x hat, a real value function. Of domain E, a subset of Rn. Notice that I'm not putting any restrictions on the domain. I'm just saying that it's a subset of Rn. I'm not requiring it to be open or connected or closed or anything. It could be any subset of Rn. Okay. Then a point P hat. Sorry, in the domain is a critical point. Of f. If E is interior to E, and the gradient of f at p is equal to the 0 vector, or P is a point where F is not differentiable. Okay, let me put some parentheses in this statement so that it's a little more clear. So P is a critical point if it's interior to B and this, right? Those have to go together. Or P is just a place where F is not differential. Okay. The two types of critical points. What does this remind you of? It's very similar to something from Calculus 1, right? Just the definition of a critical point. The only real difference here, well, there's two, I guess. Again, we replace the notion of the derivative being 0 with the notion of the gradient being 0 vector. What's the other difference between this and Calculus 1? Yeah, exactly. What do I mean by interior? Yeah. Yeah, it's not on the boundary. Right? So it could still be contained in E. The boundary, since I made no restrictions on E, for example, if E is closed, it contains its boundary. But F is not differentiable at the boundary, right? Because remember, to take a derivative, you have to take limits coming from every direction. So if your set, your domain doesn't include points from every direction of a point, you can't differentiate at that point, right? This is the same thing as like in Calculus 1, if you have a function that has a domain, a closed interval, then you can't take the derivative at the endpoints, right? Okay, good. So these are going to be really important to us because what do we do with critical points in Calculus 1? Yeah. Say again.
Test.
For what purpose?
Like contact.
To determine what is the maximum and minimum of the function, right? So we're going to develop some techniques using these critical points to find maxima and minima of multivariable functions, okay? Good. But before we do that, let's get a little more comfortable with this notion of finding these critical points and working with the tangent set to some level sets. Okay, so I'm going to pose you a multi-part example, and then this generated a lot of really good discussion in the morning section. So I think I'll have you on that you talk to your neighbors about this problem. Okay. First, let's let g of x, y, z be the function. I guess I should write this on the next line. Z minus 1 squared minus x squared minus y squared minus 1. Y. First, I'll ask you to find all critical points. G. Secondly, find points on the level set G equals 0, where the tangent plane is horizontal. And thirdly, part C. Find an equation the tangent plane at the point 3, 4, 6 to the level set through 3, 4, 6. Oh, let me just note here. Find any critical points of G. What are the critical points? Places where the level set might not be smooth. Might not be smooth. Right? So let's take a few minutes and I'm going to really encourage you to turn your desk or something. Actually talk to the people next to you. I think that will help solidify your understanding.
X. That's where the tangent line. Horizontal.
I'm sorry.
Okay, I'm hearing some pretty good discussions. Maybe we should talk about this together. Yeah. Okay. Um, so, how do we address part A? How do we find the critical points? Well, first, let's just think about the function g. G is a polynomial, right? So, it's differentiable infinitely many times everywhere, right? I didn't say anything about the domain, so we can assume that the domain is all of R3, right? So we'll only have critical points of this first kind, interior and where the gradient is 0. Yeah? Okay, so let's calculate the gradient and set it equal to the 0 vector and see what we get. So this is for part A. Gradient of G is what? What's the derivative with respect to x? Good. With respect to y. Good. And with respect to z. To z, I'm just gonna leave it like this, but yes. Okay. Good. And if we set this equal to 0 vector, well, then we're pretty limited in what we can do, right? This forces x to be 0, y to be 0, and z to be 1. Okay, so this implies that 0, 0, 1 is the only critical point. So just out of curiosity, why don't we look at the level set through this point? All we know so far is that the level set through this point might not be smooth here. Let's see what we can say about the level set when we actually compute it. Okay, so set 0, 0, 1 is defined by our function z minus 1 squared minus x squared minus y squared minus 1 is equal to this function evaluated at this point, right? So we get 1 minus 1 squared minus 0 squared minus 0 squared minus 1. So this is our level set. Our function is equal to -1. Okay, if we solve for z, what does this give us? Plus or minus the square root of x squared plus y squared, and then outside the square root plus 1. Right? What does this graph look like? What's the graph of this function? I.e., the graph of the level set g equals -1. Notice, of course, we'll have a hope of being able to graph this because g is a function of 3 variables, which is continuously differentiable. So when we look at a level set, it should be a surface, i.e. something we have a hope of drawing. And the news gets better. This is just a quadratic surface, right? This is among the examples that we looked at on that website. Yeah. That's almost right. It's multiple conic sections of a different size pasted together. Which conic section? Not forever. So the lines are involved somehow. This is like a circle. Z value, you got a circle of a different radius. Okay, so here's the graph. This is a double cone. Okay. Here's our point. 0, 0, 1. Not smooth. Right? This is a sharp point. So in this case, okay, we're gonna later on we'll do some more systematic study of how to determine if a critical point turns out to be not smooth or smooth. But as it stands right now, the best we can do is try to graph the thing and see if it's actually sharp. And here, it is the case. So this critical point happens to be non-smooth. That was just an extra curiosity. Okay, now as for part B, what does it mean to be horizontal? It's kind of a bizarre choice of terminology when you take a general perspective that no one axis is more important than the other. But generally what this is taken to mean is parallel to the XY plane. Okay, so what is another way to say that? If we're looking for places on this level set g equals 0, where the tangent plane is parallel to the xy plane. What does that mean about the gradient? Yeah. Okay, so that doesn't account for what the shape of g equals 0 is, right? Can we say something? Can we say something? First of all, how do we specify the tangent plane? Yeah. Scalar multiple of.
What was the original question?
So I was asking, the thing I asked most recently was, how do we specify the tangent plane? We look at the normal vector, right, to put it in standard form. And what we were just looking at in our previous example is that the gradient provides a normal vector under the right conditions that we're not at a critical point, right? Which we're not, right? Because there's only one critical point, and it does not lie on this level curve or level surface. Sorry. Okay, so if I want to be parallel to the xy plane, what must my gradient be? It has to be perpendicular to the xy plane. Yeah. Just a z component, exactly. It should be a scalar multiple of k hat, or i.e. a vector of the form 0, 0, c, where c is some constant. Okay, so we want the gradient of g to be equal to 0, 0, c, or some constant c. Okay, so that is to say, we will look for the points on the level set g equals 0 that satisfy this. I'm going to find values of c such that a point of this form lies on this level set. So plug 0, 0, c into g of x, y, z equal to well, let's write this out. X squared, y squared minus 1 equals 0. We're going to plug this into this equation. This is the equation that defines the level set. Okay. So what do we get? G of 0, 0, c. The c minus 1 squared, minus 0 squared, minus 0 squared, minus 1 equals 0, or c minus 1 squared minus 1 equals 0. Somebody solve this polynomial for me. What values of c satisfy this equation? Equals 2. Okay, good. And what else? Equals 2 or 0. Good. So in other words, the 2 points 0, 0, 0 and 0, 0, 2 are the points on this level curve, I'm sorry, level surface that have a horizontal tangent plane. Let's draw it since we can. Yeah. Yeah. Parallel. Yeah. It's perpendicular to the z-axis. Okay, so since we can draw this, we should. Anytime we can draw something, that is helpful to us, most likely. Try to draw it. Okay, so first let's sketch the level set. G equals 0. Okay, so what happens when G equals 0? I'm gonna just solve this for Z, right? If I want to graph it, I'll put it in kind of the standard format, right? So what do I get? I get Z equals plus or minus the square root of x squared plus y squared plus 1. Oops, sorry. All that outside the radical plus 1. What does this look like? Yeah. Not quite. Maybe go back to that website and give it a look over the quadratic surface. Yeah. Not an ellipsoid. This is actually a hyperboloid of it's 2 semicircles with curvature. It's a hyperboloid of 2 sheets. It's 2 bowls, one that opens up and one that opens down. Okay. So this is what the graph of this looks like. Okay. Here's point 0, 0, 2. Point 0, 0, 0. Look at the tangent plane here and the tangent plane here. These are horizontal. Yeah. Okay. So just bear in mind that this and this are both cross sections of the same 3-dimensional thing, the graph of G, just at different W values. Right? These are the 2-dimensional cross section of some 3-dimensional thing sitting in R4. So we're almost out of time. What will we do for part C? I'm going to describe the general process. Yeah. Yeah, exactly. That part C is the easiest part. It's the most mechanical. You don't have to really draw anything or think of anything. You can, but it's just applying the formula, right? That is to say, let's just write it down. Radians of G evaluated at 3, 4, 6 dot x minus 3, x minus 4. Oh, sorry, y minus 4, z minus 6 equal to 0. Okay, so you can calculate that out if you like. Okay, good. So we're almost caught up to where the morning section is. This won't be a problem at all. So don't forget the quiz is at 3 and you'll have 24 hours to do it. Have a good long weekend and I'll see you next Wednesday. Yeah. You could program something like that in Mathematica, which is free for Northeastern students. Or you could probably bring something up in GeoGebra. MATLAB also free for Northeastern students. That's a good thing to do. Yeah.
Question.
Yeah.
For some of your definitions, you say thing as a function. And does it always follow the fact that the function was passed VLT?
I'm sorry, what is the deal?
The vertical line test. Is that's how we define a function in like Calc 1 or something?
Oh, yeah, so, for example, remember we had a parameterized curve that crossed itself?
Yeah.
That doesn't have to.
I noticed before, and I just always forgot to bring it up.
Yeah, so, right, that's kind of like a limited idea of what a function is. The general principle is that, it's, not one to many. There's not more than one output value for a single input.
Okay, so
Now,
just every X has one line, but like, not sort of really.
so the deal with that curve was, remember, it was parameterized. So the parameter value was different. And we were just plotting points in, so that was actually two functions that were describing how to draw it. So it's still a function, but that definition of what the graph means doesn't
Yeah.
apply. Yep. Hey, what's up?
I just have a question.
So I don't actually know the answer to that, what the answer should be. So why don't I like try to talk to the DRC and see what they say? I'm not sure what the right answer is.
Okay. I just
Um,
wasn't sure because I know for like quizzes where it's like a sit down in class 20 minutes, they say no,
they say no, yeah, okay.
because that would be like you know, extended time,
Yeah,
which is like a different thing.
mm,
But for like assignments that are take home that are like you have 24 hours to do it,
mhm.
they say like, yeah, the 3 days apply.
Oh, if they, if
So
they,
it's sort of in between.
yeah, yeah. How would you feel if we just called it like 2 days instead?
That works for me.
Okay, you just want to turn it in by 2 p.m. on Saturday.
I'm gonna try to get it done today. It's just
Okay.
like sometimes things get in the way.
Yeah, that's fine. Yeah, and if that ends up, if that doesn't work well this time, we can talk about maybe even more. But yeah, see what you think. If 2 is reasonable, then I would prefer that. But if you need it, then you can have it.
Okay, thank you so much.
Yeah.
Have a great day.
You too.
Or weekend.
Yeah.
So why like show like to you like solve for Z, you get also this equation here.
So when I solve for z, when I set g equal to -1, I get this equation. When I solve for z, when I set g equal to 0, I get this equation. So yeah, that's the key difference, right? That I'm changing not the set, where I'm taking the cross section.